Okay, so welcome back. Today we're going to essentially finish up chapter 2 in the book, and then next week we're going to move on to determinants and eigenvalues. So let me just say where we were last time. Well, we had a map, which let's just say goes from Fn to Fm. Same thing will work if it goes between any two vector spaces. Okay. Then we had another map, which we got from looking at the transpose of the induced matrix, which goes the other way. Okay. And we worked out relations between the dimensions of the kernel and the image of A and A transpose. Okay, so the most important fact was the rank nullity theorem, or I forget what I called it in the last lecture video, but it was the fact that if you have that the dimension of the kernel of A plus the dimension of the image of A was equal to n. Okay, and similar things for the transpose map. Okay, so today I just want to start with a little application by noticing that we have other maps naturally available to us, right? Once we've defined A and A transpose, then we get two maps for free by looking at their composition. Okay, so we have two maps, A transpose, which goes from Fm to itself, and A transpose A, okay, which goes from Fn to itself. Okay, so notice, and so it's going to turn out that in some sense these are nicer than their component pieces. For one thing, they both go, they're both square matrices, which is nice. Okay, so they go from a fixed vector space to themselves. So notice that they're also symmetric. Okay, so A transpose A and A transpose is symmetric. Okay, because we have the fact that A transpose A, if I take its transpose, this is A transpose A transpose transpose, which is A transpose A. Okay, so from any matrix, in some sense, you can multiply it by its transpose to give you a symmetric matrix. So let me just give you an example. Okay, so A is going to be 1, 2, 3, 4, 5, 6, and A transpose then is 1, 3, 5, 2, 4, 6. Okay, so I'm just going to do A transpose A, since that's a 2 by 2 matrix. All right, this is 2 by 2. So this is exactly, well, write it out, 1, 3, 5, 2, 4, 6. Okay, so this is, well, let's see, so I get 1 plus 9 plus 25, so I get 35. Here I get 4, 16, 36, I get 56. Here, for both of these, I get 44. All right. So I get a symmetric matrix. Notice that every entry in A transpose is something we've seen before. Saw last time. Okay, so last time I defined V perpendicular to W if and only if V1 W1 plus V2 W2 up through Vn Wn is equal to 0. All right. And this is exactly what you're doing by taking the product of these matrices. Okay, so if you look at 35, 44, 44, and 56, what you'll see is what you're checking for the matrix 1, or the vector 1, 3, 5, and 1, 3, 5. Right, we got 1 squared plus 3 squared plus 5 squared. Okay, so that corresponds to this entry. So we're taking the first column and checking this expression with itself. Similarly, the 56 was obtained by looking at 2, 4, 6, 2, 4, 6. Okay, and then we're looking at 1, 3, 5, and 2, 4, 6 to produce the 44. Okay, and it doesn't matter which order you do it. So this is a special case, or I guess these values are a special case of the dot product v tensor, or v dot w, okay, which we'll talk about in a couple of weeks and kind of give more background and structure to what it is. Okay, but this is at this point what the matrix multiplication when you're doing A transpose A is doing. Okay, you're just checking all of the column vectors of A and looking at various combinations of this form. Okay, so this justifies, so maybe I should say what this also tells you is that the diagonal entries of A transpose A are greater than or equal to 0. Okay, this is just because if I do this for any vector, I'm getting v and v, I'm getting v1 squared plus v2 squared up through vn squared, which is greater than or equal to 0. And the off-diagonal entries of this matrix are 0 if and only if different vectors, different columns in A are orthogonal. Okay, so are perpendicular. So if you take any two columns, they should have perpendicular images, right? This is exactly just this condition. Okay, so the off-diagonal entries are measuring the dot product of different vectors in the image of A. Okay, so what this really does is it justifies something that I said in the practice midterm. Actually, it justifies the notion of orthogonal matrix. Okay, so where A transpose is A inverse, so we get A transpose A is equal to the identity. What this means is that under A, and notice here, this has to be a square matrix for this to make sense, okay, since we're assuming that the transpose is the inverse. So under A, the image of, say, the standard basis vectors in Rn are all perpendicular, okay? And for any of them, if you look at the expression A1 squared plus AE2 squared up through AEN squared, you get 1, okay? So sometimes this is called an orthonormal collection of vectors. I'll just give an example. All right, so if you look at the vectors 0, 1 and then hit them with the rotation, then of course this preserves the angle, right? If you rotate by alpha, you preserve the angle between them, and you preserve the sum of their squares, okay, because you're mapping things to the unit circle, so the sum of the squares is 1. And you can see, like in the matrix, that this satisfies AA transpose. Oh, maybe I'll make that a little larger, because we have cosine, cosine, negative sine, sine. Okay, and you can check that if you take the transpose of this, you're exactly getting the inverse of the matrix. Okay? So this is just shows that, well, the geometric picture here is somewhat represented, or it's a good geometric picture and represented by this property of these matrices. Okay, so in general, of course, you might have A transpose A is not the identity, but it's still nice. So it has kind of nicer properties than A, even if A is a square matrix. Okay, and so we'll see this soon when we talk about eigenvalues and diagonalizing matrices. Okay. Okay, so let me go back to an example that we've used kind of throughout the corridor, and that's graphs, and there are corresponding some matrices that you can attach to them. Okay, so I'll just give you another picture here. So we have some graph. Okay, maybe we'll do something like this. Usually I'm going to assume it has directed edges. Okay. And then we associated to it a couple operators or matrices. All right, so let me do the first one was the boundary operator. So this went from functions on edges to functions on vertices. And what it did was send, well, again, on a basis, what it did is it sent the 1 here and zeros on every other edge went to 1 and minus 1, okay? That was, and then you extend it linearly to any function on the edges. The other one you had was the map, which goes from vertices, or functions on vertices, to functions on edges. Okay, and in this case, again, I'll just say what it did on a basis. So if I put a 1 on this vertex, maybe the local picture looks something like this. Okay, a 1 on this vertex and zeros everywhere else, it went to this picture where you assign 1s and minus 1s to the edges containing it. Okay, and let's see, so here it assigns this a minus 1, it assigned it a 1, and then assign this a 1. Okay, so the way that you can check this is if you concentrate on a single vertex and a single edge, what it should do is this 1 should map to a 1 here, and then the boundary operator sends it back. Okay, so here it goes to a minus 1 because the boundary would send this to 1 on this vertex. Okay, so it turns out that, I'll write it this way, it's slightly more natural to go like this, that the boundary is just the transpose of the co-boundary, or the delta. Okay, all right, this is usually called boundary and co-boundary for reasons I won't get into. All right, so it turns out that that these are transposes of each other. All right, and now it's natural to look at, well, you could do either boundary and then the co-boundary. I'll just do, I want to look at this and then this. Okay, so we're looking at delta, delta transpose, and this goes from the vertices to the vertices. Okay, so let's try to figure out what this thing actually does. Okay, that's a good thing to figure out. So I'll do the last example here. So So I had a 1, and I'll just put some random orientations. Okay, so now I hit this with my delta. Okay, so I get a 1 here, a 1 here, and a -1 here. Okay, now I take the boundary. All right, so what do I get? Well, I've cooked it up in such a way so that this edge will contribute a 1, this edge will contribute a 1, and this edge will contribute a 1. Okay, so I'll get a 3 on this vertex. Then I get -1, -1, -1 on these vertices. Okay, so that's my matrix, or that's my composition, now seen as a map between the vertex set and the vertex set. Okay, so what is this doing? Okay, so notice that this 3 here corresponds to the number of edges which contain this vertex. This is usually called the degree of V. Okay, if this was a vertex V, so just the number of edges containing it. Okay, and this is going to be picked up by the way that I've made my orientations, or my assignment of 1s and -1s. No matter if I'm facing inward, or if I have an edge going inward or an edge going outward, if I do the boundary and then the co-boundary, I think I said that in reverse. If I go from edges and then I go to vertices, I automatically assign a 1 here. Okay, so what this does is it just counts the number of vertices no matter how many there are. So, if I see a 1 here, it doesn't matter about the orientation of the edges. I know that, there will be a 7, after doing this, I'll get a 7 there. Okay? So a nice way to say this is that there's what's called a degree matrix, D, okay, which is diagonal, okay, and it just assigns to every vertex its degree. Okay, so here you see the degree of V. So in this matrix here, it would be exactly 3, depending on the order of the vertices, I would get 3, 1, 1, 1 for just this tripod graph here. Okay? The other thing that this is doing, so there's other values here that this map delta transpose delta is accounting for. It's also, you're getting -1 values at every vertex adjacent, right? So it's easy to see that if I start with a 1 here, and I look at a vertex which is not adjacent to this vertex, if I was 0 here, and I'll be 0 afterwards, right? I haven't gone out far enough in my graph to notice this, okay? So it turns out that delta, which I'm going to call, which is my notation for just delta transpose, is precisely D minus A, okay, where this is the degree matrix. Again, this is just, looks like the identity, but it might have higher values on the diagonal. And this is the adjacency matrix of the undirected graph. Okay? Okay, so just 1s and 0s, or you get a 1 for every edge connecting vertices. Okay? But the direction doesn't matter, right? So I get, if this was oriented, you see it didn't matter if I was oriented away or oriented towards this vertex in the center, I still produced a -1 for both entries. Okay? And this is true in general. Okay, so this is usually called the graph Laplacian. okay? And somehow it's not carrying much, it's not carrying much more information than the degree or the adjacency matrix, but somehow it has nicer properties, okay? So what are some nice properties here? Well, for one thing, its definition is based on an orientation of the graph, right? We had to fix, if we wanted to define these maps, we had to define an orientation on every one of the edges. But it is independent of it, right? So what you get at the end after you take delta delta transpose is something which depends only on the shape of the graph, not on the way that you orient it. Okay, so that's kind of nice. Okay, and again, that's something that is not true for the adjacency matrix of a directed graph. Okay, it also has the same nice properties that you would expect just from a general symmetric matrix. Okay, so it has symmetric entries. Positive diagonals. Okay, and it will turn out, this is kind of a deeper fact, but something that's kind of useful, is if you look at the vector, so you look at delta of v, so now this is some in C0 of gamma, so some function on the vertices, if it ever happens that you just obtained this function by multiplying it by a real number, v is called an eigenvalue of delta. Okay, so what this means is that when you apply delta, you just get a multiple of it. It implies that this delta is greater than 0. Okay, so you can only send vectors to positive multiples of themselves, not negative multiples, and that's going to be leads to nicer behavior for this matrix. Okay, and I should have written here, because this could be 0. In fact, this is my next question, which I'd like you to think about, is what is the kernel of this graph Laplacian as, an operator on functions of vertices? Okay, so there should be a natural function or class of functions which is has delta f being 0. Okay, maybe I'll just give you a picture just so you can think about what delta is actually doing. Okay, the idea is actually you should imagine fixing a vertex. I'll just start with at a basis vector. Okay, then what is delta doing? Well, your first one sends this to 2, -1, -1. So this is one application of delta. The second application, well, let me see. So at this vertex, we get a contribution. So we get a contribution of 1, -2, 1. Similarly here, we get 1, -2, 1. Here we get 4, 2, 2. Okay, so we get, -2, -2. So we end up with 6, 4, -4, 1, 1, -4. Okay, so you get some nicely oscillating values. It turns out if you start looking at iterates of this operator, it starts telling you interesting stuff about the matrix, the graph. Similarly, if you start looking at the eigenvalues of this, you'll also end up discovering interesting properties about the graph, okay, that are kind of hard to access through graph theoretic methods. Okay, so this was a long aside, but hopefully it's something that I hope is interesting, but also is useful to think about just in terms of linear algebra, not just thinking about graphs. Okay? So let me now kind of switch topics to the last topic in chapter 2, which we have seen before, but I just want to make more explicit. Okay, so these are change of basis matrices. Okay. So here is, again, something that I've kind of mentioned a couple times throughout the lectures. So we have a transition matrix. Okay, so what this is we have a vector space V, two bases, which I'll call, I guess, X and Y. Okay? And then you get a transition matrix, which I'll call IXY. It goes from V to V, and all it does is it represents the identity transformation with respect to X in the domain and Y in the range. Okay? Okay, so what this is doing is you're taking a basis vector for X and writing it in terms of Y. Okay? So in the sense that if I look at IXY, and I look at the kth column, okay, and I say what is here? Well, this is precisely the kth basis vector for X written in the Y basis. Okay? Okay, so note that we also have a matrix Y of IX, which does exactly the same thing, but writes basis vectors for Y in terms of X. And we have that this is equal to XY inverse. Okay? So what we're doing here is we're first writing Y, or writing a basis element XI in terms of Y, okay, and then writing that in terms of X. Okay, but you know exactly what that is, right? If I take in terms of X, well, if I start with a basis vector, I write it in something in terms of Y, it might be complicated, but certainly when I write it, that same vector in terms of X, I know what I get, right? I just get XI back. Okay, so that spits out the identity matrix, so therefore these two matrices are inverses of one another. So usually, or kind of a common example, is when one of the bases is standard. Okay, so maybe you're just in f to the n, and your basis vectors will be the standard basis vectors e1 through en. Then for any other basis, b1 up through bn, well, we know how to write the b sub i's in terms of the e sub i's, right? So we write, maybe I'll call this one e, this one b. We know e be, okay? This is just the matrix with the b's and the identity, okay? So this is because we know how to write the b sub i's in terms of e. Okay? So that's, and you can think of this as well as just you're sending the standard coordinate vectors to the basis vectors of B. Okay, going the other way, of course, so if you, it just corresponds to writing the inverse. So if you write the basis vectors E sub I, the standard ones, in terms of the basis V, this is just taking the inverse of a matrix. Okay, so let me do an example. So actually, I'll do the general case in R2, say, or F2. Okay, so we're going to have two bases, which I'll call AC and BD. Okay, that'll be one, and then G and FH. Okay, so I tried to do it in the way that I would get AC, BD, and EFGH. Okay? Okay, so this sends, maybe I'll say it this way, this sends the standard basis to the vectors A, B, C, D. This sends the standard basis vectors to the basis E, G, F, H. Note I have to assume here that AD minus BC and EH minus FG are both non-zero. Okay. Then to get the transition matrix between these two bases, okay, well I just do the inverse here and then apply here. Okay, so if I plug in D A minus B minus C all divided by AD minus BC, so we got that for the general inverse, times EF GH. Okay, so this sends AC goes to EG and BD goes to FH. Okay, so in other words, what this does is this is writing this basis in terms of this basis. Okay, so that's the general formula for transitioning between two matrices. You can kind of hop between the standard basis, and then it comes down to essentially the hard part is computing the inverse of one of the matrices. Okay, so now what we want to do with these transition matrices is we're going to have T going from V to W. We have bases X and X tilde here, Y and Y tilde here, and what we would like to do is compare T, or the matrix for T, so T's matrix, with respect to the XY bases and the X tilde Y tilde bases. Okay, so I'm going to let T YX and T Y tilde X tilde denote the respective matrices. Okay, and then we have the formula that if you want to write Y in terms of this, or write T in terms of this new basis X tilde Y tilde, well, you start with the matrix for T in terms of Y and X. Then what you do is, well, you first, so you can think you're starting with the basis for X tilde, you're writing X in terms of X tilde, you're then using the basis for X and the basis for Y, and then finally you're turning the basis for Y and writing it in terms of the Y tilde. Okay, so that's the formula for the general relation. Okay, so let's do an example as a sort of sanity check so we can check that we have the right ordering, for example, these matrices. So let's look at the transformation T, which goes from R2 to R2. So I'll write it in the standard basis. it's going to be given by the matrix 2, 1, 1, 2 from the homework. Okay? You can then take a basis, another basis, which is 1, 1, and 1, negative 1. Okay? So that's a perfectly good basis for our 2. And this has the nice form, so in terms of t with respect to this basis is just 3, 0, 0, 1. Okay, so 1, 1, remember 1, 1 goes to 3, 3, so you're just multiplying this vector by 3. 1 minus 1 stays 1 minus 1. So this is just times 1. Okay, so, and then the claim, so let's just check what this is saying. So I'm claiming 3, 0, 0, 1 is equal to 2, 1, 1, 2. And now we want the matrix. Notice we're in a special case where the basis x is equal to the basis y, right? They're both the standard bases. And x tilde is equal to y tilde as well. They're the new basis here, okay? So to go from the new basis from the old basis, well, we know how to get, we know this one, okay? This is just the images of our vectors, so 1, 1, 1 minus 1. There is a discrepancy on flipping the columns, so I could have switched the columns. I would have switched which basis vectors get sent to which. And then I have to take the inverse of this matrix, which happens to be negative a half times negative 1, negative 1, negative 1, 1. Okay? So let me just pull this out. Okay, and we can check that if we multiply these matrices, we're getting, let's see, negative 3, negative 3, negative 1, 1, okay? And then this is equal to negative 6, 0, 0, negative 2, okay? And luckily for us, there is this minus a half feature, so we got exactly, so times negative a half, we get 3, 0, 0, 1. Okay? So this is just sanity check. The formula works. You want to write something in terms of this basis, which has a nice, much simpler form than the standard basis. So you first are taking this basis back to the standard one, then multiplying, and then bringing it back. Okay? Notice here that there's lots of different ways that this could have gone. So we wrote as matrices, okay, we're writing something like B is QA Q inverse, okay? Notice, for example, that if I take, say, any matrix with PB equaling BP, okay, so any matrix which commutes with B, well, then I can write PB, P inverse is B, just another way to rewrite that formula, and therefore B is also equal to PQA PQ inverse. Okay? So you can't take, any matrix here for Q, obviously. It has to send the basis to the right basis. Okay, but you can do it, it's certainly non-unique. Okay, so this is a diagonal matrix. There's a decent number of other matrices that commute with it, okay, which are invertible, and you're allowed to kind of add those on. So maybe I should just emphasize here, this is PQA Q inverse P inverse, okay? And there's this non-uniqueness now between these various forms. Okay, so this motivates the following definition, okay, which will continue to come up now. Okay, so we say that a matrix A is similar to B if there exists an invertible matrix Q so that A is equal to Q inverse BQ. So notice this only makes sense for invertible matrices. Sorry, square matrices. Okay, since we're assuming that Q is invertible. If it's not square, there's a similar definition. So if A is n by m, okay, then A is similar to B if A is Q inverse AP, okay, where now this is n by n and this is m by m, okay? But both P and Q have to be invertible, okay? So even though not stating P inverse here, we're still assuming that P is an invertible matrix, okay? So these similar matrices represent the same linear transformation, okay? So both of these P and Q matrices you can just think of as, and I wrote A here, now this should be B, okay? So this is, you should think of P and Q as change of basis matrices. A and B are just different matrices for the same transformation T, okay? So therefore, they have a lot of the same properties, okay? So and hence, have the same rank. If it's square, they have the same trace. We'll see next week they have the same determinant. Okay, so essentially, I mean, again, it's the same transformation. You're just representing in different ways. So kind of all of the properties of that transformation should be the same. Okay, so you can check, and this is a useful exercise, that similarity is an equivalence relation. Okay. So therefore, you can think of the set of linear transformations as the same as the set of matrices up to this similarity equivalence relation. Okay, so if you look at something like MNN, or it doesn't have to be square in this case, something like this, you'll get exactly the space of linear transformations. It's also, useful, so this is like another reason that the trace and other invariants, like the determinant, are important, okay? So it can detect whether two matrices are similar or not. Well, so it's not an if and only if, but at least it gives you a condition for when they're not going to be similar, right? So now you can imagine when you're doing work with matrices, if you have some complicated matrices A and B, you would like to know some invariants so that you can distinguish if they're, actually just representing the same linear transformation, but maybe B is doing it in a super complicated basis. So it looks, quite complicated, but it's actually in another basis quite simple. Okay, so we'll see that next week. We're going to get into the determinant, which is another invariant will detect this. And then we'll also get into trying to put these matrices, choosing the right basis, so that for any matrix you can find a similar matrix which has as nice as possible a form. Okay, so I'm gonna stop here. Thanks.